Hello, I'm Laser, and this episode I'm going to show you the Edmonds-Karp's algorithm. So what's this algorithm for? Well, it tries to find the maximum flow through a directed graph. Maximum flow is trying to push the most material from a source to a sink. To further dive into the detail of maximum flow itself, we need a quick recap on graph theory. Graphs contain a set of vertices and a set of edges. Vertices are joined by edges. Edges can have direction, meaning that it is possible to go from vertex 1 to vertex 2, but not the other way around, unless the edge itself is two-way. Edges can have weight, a number that denotes a value that is elsewhere specified. For example, it could be distance. Boy, that was a mouthful. If we take a look at this graph again and add some weights to each edge, which in this instance denote their capacity, our problem is what is the maximum amount of material we can send in a single go from the source to the sink. It's not as easy as looking at the outgoing edges from the source and saying that their capacity total is the maximum flow, because further edges down the line might not have the capacity to deal with that amount of material. Whatever flows into a vertex must flow out. Exceptions for the source and the sink, obviously. So what exactly is flow and capacity? Just before I get started, let me go over a little bit of notation. These are regular vertices. This is a source, and this is a sink. This is how I denote flow, and this is how I denote capacity. I separate them with a pipe. And finally, this is a directed edge. Got it? Okay, great. Let's start with capacity. The capacity of an edge that goes from vertex 1 to vertex 2 is the maximum amount of flow that can be pushed over an edge. The flow is defined as the current amount of material being pushed over an edge. The flow cannot exceed the capacity and cannot be negative. Also, as stated earlier, what flows into a vertex must flow out, meaning the net flow over a vertex should always be zero, the net flow being the flow entering minus the flow exiting a vertex, unless it is a source or a sink. Note this has nothing to do with capacity. The edge capacity entering a vertex does not have to equal the capacity exiting a vertex. Finally, a flow network has to have certain properties for Edmonds-Karp to work. These are: the network must have a single designated source and sink, the source being where material flows from and the sink being where material flows to. Edges must be directed. It's no use having an edge without direction because you can't really transverse without direction. Edges must be one way only, and edges with zero capacity are ignored and removed. Now that's a pretty strict subset of graphs, but not to worry because you can convert directed graphs to meet this form. Let's take an example graph which we need to convert to be a flow network. Here's a simple 4-node network that breaks one of each of the properties I listed. For starters, this graph has multiple sources and sinks. Focusing on the sources, to fix this problem you create a new vertex that will be your new source. You link this new source to all previous sources with edges directed out and make the previous sources regular vertexes. But what about the capacities of all the edges? Just make them infinite. You can use this exact same method to fix the sink problem as well, just have the edges going to the new sink. What about undirected edges? Well, the best assumption to make is that they are two-way edges. Now this leads us into the problem of an edge needing only a single direction. To fix this, just create a new vertex for one of the other directions to go down. The final thing to do is to simply remove all edges with zero capacity, and that's it. We nearly know everything we need to perform Edmonds-Karp. Just one final thing to understand: a residual network. The concept of a residual network is a little tricky to explain and justify, but I'll be as concise as I can. When you push flow along an edge, due to how max flow is calculated, you can elect to push something back along an edge. Now of course the rules we've established earlier is that you can only push in one direction over an edge, but this isn't actually what's happening. Here's a little proof of concept. Say I want to increase the flow on this part of the network. Ignoring where the source and the sink are, I push 7 up this edge. This flow now has nowhere to go because the only way out from the vertex it's arriving to is already full. But I can't undo a previous push to give this flow room. So what's actually happening is I'm diverting flow from one vertex to another. This helps to overall maximize flow in the network. The residual network itself doesn't have the restriction of only one edge per pair of vertexes. The edges in the residual network are calculated like this. In English this says, for the residual network we construct a new set of edges from every possible pair of vertexes from the original graph, with positive capacity. Some of the edges are made with the unused capacity from the original graph and some edges are made from the flow just reversed. Note that the edge weight is always the capacity on the residual graph. A quick example, suppose I have this really simple network here with just 2 vertexes. I have an edge with capacity 12 and I'm pushing 7 along it. Getting a residual graph from this, I see that I have a capacity of 5 left over that I could have filled, so I make this an edge in my residual network, going the same way as the flow in the flow network. I then look at the 7 flow and reverse it in my residual network, and there we go, I've got a residual network. So now we can finally start calculating maximum flow. Here's the algorithm. You take a graph with a source and a sink. You initialize the flow in the network to 0. You create a residual network from that flow network. While there exists a path from the source to the sink in the residual network, called an augmentation path, push the maximum amount of flow you can along the path in the flow network, called the augmented flow. After the push, update the residual network based upon the current flow network. When the algorithm finishes, we have got our maximum flow. How do we choose our path? Well, we choose the shortest path, from source to sink. The way to find the shortest path involves another algorithm called breadth first search, but don't worry about that for now, and just remember that in Edmonds-Karp we pick the shortest path with every iteration. And just to be clear, the shortest path is not a path with the least edge weight total, and instead is the path that uses the least amount of edges. It's worth mentioning that Edmonds-Karp is based off something known as the Ford-Fulkerson method. The Ford-Fulkerson method is nearly identical in every way to Edmonds-Karp. The only difference is that Ford-Fulkerson's augmenting path is any path, and Edmond-Karp's augmenting path is always the shortest path. So let's work through a problem together. Imagine you work for a cider shipping company based in Bristol. You want to maximise the flow of cider shipments from Bristol to London through various transport routes. Here is a graph of the maximum number of crates you can ship between certain cities. What is the maximum amount of cider we can ship? Well, let's take this graph and follow the algorithm. We have the graph, a source and a sink. We create a flow network from the graph, initialized to 0. We create a residual network from the flow network, which ends up looking exactly like the input graph. Now we can begin the augmentation process. Let's start by finding the shortest augmentation path in our residual network. First, we start with a fairly squiggly path through the middle here. It has a length of 3 edges and goes from S, V3, V4, T. Note that when there is a tie between paths for shortest length, you may arbitrarily pick a path. Since the minimum capacity of this path is 3, we augment 3 flow through the same vertexes in the flow network. We then update our residual network based upon the flow network. What the residual network is saying is you can choose to pull 3 flow back along this path, or push the remaining capacity of all these edges. Since our shortest path had a length of 3, the next path must have a length of 3 or greater. Let's move on to the second stage. Here is our next shortest path, also with a length of 3. It goes from S, V3, V5, T. The bottleneck capacity is 6, so we augment this in our flow network. Notice how between vertex source and V3, we add this flow with the previous flow. Finally, we update the residual network and iterate again. Our shortest path has a length of 5, and goes from S, V1, V2, V3, V5, T. We push this new flow through our network and update the residual network. Now let's pause for a moment. If you were to only look at the flow network, you would think there are no more paths through which we can push our flow, but the residual network tells a different story. Between V3 and V4 there is flow we can push back that makes room for more flow in the network. This is found by the algorithm in the residual network because it creates a path from source to sink with length 6. Our path goes through all vertexes S, V1, V2, V4, V3, V5, T. It has a bottleneck of 3, so we can augment this through the network, undoing the flow across V3 and V4. There are now no more paths from source to sink in our residual network. We have found the maximum flow, which turns out to be 15 crates of cider. Not bad for a night out. The worst case time complexity of this algorithm is big O number of vertexes times number of edges squared. This is because it takes big O number of edges time to find the shortest path, and this operation has to be done at most number of vertexes multiplied by the number of edges times. This video was made for the Data Structures and Algorithms module for second year computer science at the University of Bristol, created by Lazaros Donmez and supported by Elias Abi Sab. Thanks for watching.